morning.
Any questions at all before we get started? Take that as a no. Just a couple of things. One, I'm expecting an estimate for tree service today. They're supposed to be here at 10, but sometimes people show up early, so I'm sitting outside on my deck oriented so I can see down my driveway in case somebody shows up early. So if they do, I might get interrupted for a minute or two. I'll just mute the video or mute the audio at that point. My plan was to try to get done a little bit early today anyway. I just want to finish up the stuff on diagonalization. We'll start new stuff on Monday, but I do want to give you a test next week on next Friday. So I want to spend a little bit of time talking about what I expect for that. So we'll get to that when I get to that. So let's just finish up the stuff with diagonalization. So we talked about that last time. So I just want to do a couple more examples. Because I mentioned last time that if we can find n linearly independent eigenvectors, then we are able to diagonalize. But in some instances, we won't be able to find n linearly independent eigenvectors. So we'll have an instance here where we can and we can't, and we'll see what the differences are and talk a little bit more about that. So let's look at this example I have up here for this matrix B. So remember again, when we're going to diagonalize...
No.
Yes?
I don't think you're screen sharing.
Oh, you're correct. I am not screen sharing. Thank you. You didn't really want to see what I was writing, did you? Here we go. All right, so that better? I hope.
Yes.
Okay, cool, good, thanks. All right, so remember last time when we talked about being able to diagonalize a matrix, the first thing we have to do is find the eigenvalues and the eigenvectors. So let's do that for this particular matrix. So remember, to find our eigenvalues, the first thing we're going to do, I'll stay with red, why not? First thing we're going to do is subtract lambda off the diagonal. Take the determinant of that matrix and set it equal to 0. So we talked about how we could do this in the calculator and help us find the eigenvalues. This one's not so bad though, since I've got that row with a couple of zeros in it. This one's not so bad to be able to do the determinant. The only non-zero piece we'll have is that 3 minus lambda. It's a positive 3 minus lambda, because that would have a plus sign associated there when we do the expansion by minors. We've got a 6 minus lambda, a 2, a negative 6, and a negative 1 minus lambda for the minor that's left. And then when we do the determinant here, since it's a 2 by 2, that makes life much simpler. So I have that 6 minus lambda times negative 1 minus lambda, and then minus a minus 12. I've already got the 3 minus lambda out in front as a factor. So I just need to expand this out and then try to refactor it if I can. So let's see, we have lambda squared. I get a plus lambda and a minus 6 lambda, so that's minus 5 lambda. I get a minus 6 and a plus 12. So I get a plus 6. And then that refactors nicely. And then we can see the roots here pretty easily, but I'm going to rewrite this just quickly because I want to talk about a particular concept that we have. So I can factor a negative out of this first factor, and I'm left with a lambda minus 3, so I actually have 2 of those. So I've got a lambda minus, or a negative out in front, a lambda minus 2, and a lambda minus 3 squared equal to 0. So notice that I get a repeated root here for this polynomial. I've got that lambda minus 3 squared. So we don't have, in this case, 3 distinct eigenvalues. In the previous example that we did at the end of class last time, we had 3 distinct eigenvalues. And remember, when we have distinct eigenvalues, we know we can find linearly independent eigenvectors, because we know that an eigenvector associated with one eigenvalue is linearly independent from any other eigenvector, or any other linear combination of any other eigenvector from different distinct eigenvalues. So we know we have something that's a little bit different here with the eigenvalues going on. Now, this is not to say that we can't diagonalize, it's just that we might not be able to. As soon as we start getting repeated roots, we may not end up with enough eigenvectors to be able to do the job. And that's all going to depend on when we go through and try to find our eigenvectors. Okay? So, just to add in a... Yes?
Would those be negative, though, since you have the negative out in front?
I could divide both sides by the -1 and get rid of the negative, and it wouldn't change the roots. Okay. Yeah, so
Okay.
that constant out in front is not going to change the roots for us. All right, so let's see about finding these eigenvectors and see if we are able to diagonalize. So again, since we have a 3 by 3 matrix, we're going to need to have 3 linearly independent eigenvectors. All right, so let's do the lambda equal to 2 first. We would have the matrix 4, 2, -1, and then we would have -6, -3, 2, and we would have 0, 0, 1. And let's see. First thing I notice is that if I take, what is it, 3 halves times the first row and add it to the second, I'm going to get zeros there. I guess I haven't done this in reduced row echelon form yet. I'm doing 3 halves row 1 plus row 2 replace row 2. Right? I did that right?
Wouldn't the last one in row 2 be 1/2?
Oh, yeah, it would be a 1/2. Thank you. Because I would have -3 halves plus a 2. Yep, you're right. I'm going to get a row of zeros there eventually, but thank you, Nick. I appreciate that. Okay, so now, to finish this off, I would need to do a 1/4. This is why typically I use the calculator at this point. 1/4 row 1, replace row 1. And then I would also need to do a couple more. I'm going to take that, I'm going to do a bunch of them at once. I would swap row 2 and row 3. And then I would use this one right here to get zeros everywhere else. So I would do, at that point I would do row 2 plus row 1, replace row 1, and I would do -1/2 row 2 plus row 3 and replace row 3. That's after I would do the swap, by the way. So I'm going to do 4 row operations at once. That should be your reduced row echelon form. And if somebody's got their calculator and wants to type it in and check and make sure that I actually have that correct.
Yes, that is correct.
Oh, wonderful. Thank you. I expect that you will be using your calculator. I just didn't feel like switching screens. I was being lazy. All right. So now we can see what the solutions have to be. I see a free variable there in column 2. So I know that would be a 1. Once that's a 1, this top one would be a -1/2. And then the third one is 0, because this says x3 equals 0 there. So I can use this for my eigenvector, or I can use a scalar multiple. And like I mentioned last time, I typically like to get rid of the fractions if I can. So I would probably use -1, 2, 0 for that one. That's just personal preference. If you want to leave it as fractions, it literally does not matter. Heck, if you want to add more fractions in there by multiplying by a scalar, have at it. You can do whatever you'd like. It doesn't matter. All right. So we've got one eigenvector associated with the one eigenvalue. Let's see if we can do the other. So the other one was lambda equals 3. Need to subtract 3 off that diagonal. I need to remind myself what the matrix was. So we got 3, 2, negative 1 for that first row. We've got negative 6, negative 4, 2 for the second row. And then we've got 0, 0, 0 for the last row. All right. Now correct me if I'm wrong, but that second row is 2 times, or negative 2 times the first row, right? All right, so if I do the reduced row echelon form here, see if I can get through this without making a mistake. Definitely have 0, 0, 0 in the last row. I'm going to get 0, 0, 0 in the second row if I do 2 times the first row and add it to the second. And then if I multiply by a 1/3, I should get that in my first row. Okay, so before we go and write down the eigenvectors, let's look at the way the characteristic polynomial factored and how many free variables we have here. So we noticed that we had that lambda minus 3 had that 2 for the multiplicity, right? We had 2 factors that were lambda minus 3. So that was said that the multiplicity there was 2. When we used that word multiplicity back in algebra class, it's just the power that's on the factor that gives you the root. So that's where we get multiplicity, 2. Now over here, we have 2 free variables. And that's a good thing for us because we want 2 free variables because we're going to need 2 more linearly independent eigenvectors to be able to diagonalize this matrix. So when we write our solutions here, we would have an S and a T. One of them is representing the second coordinate, one's representing the third coordinate, and those are independent of each other. And then the first component has a negative 2/3 there, and it would have a 1/3 here. Just writing out the solutions. So now, I know that from work that we've done before, I know that those are linearly independent. So if I use each of those for an eigenvector, or a scalar multiple of each of those for an eigenvector, they will be linearly independent. So from here, and again...
Wouldn't the 1/3 be negative?
Remember, we have to we imagine that augmenting of zeros here.
Oh, yeah.
And then we would change the sign to the other side. Yep. So if I like to clear my fractions. So one of the eigenvectors here would be negative 2, 3, 0 that I would use, and the other one would be 1, 0, 3. So now I have my 3 linearly independent eigenvectors. So you can choose your matrix then, P. I'll write that over here. Our matrix P that we're using to diagonalize will be negative 1, 2, 0, negative 2, 3, 0, 1, 0, 3. And our diagonal matrix D will be, well, the negative 1, 2, 0 is associated with the 2, so the 2 will go here. These other 2, the next 2 columns, were associated with 3. So those 3, well, that didn't look like a 3 at all. Those 3s will go down your diagonal, and you'll get zeros everywhere else. And so if you can check now that if you do P inverse times A times P, you really should get D. And like I mentioned last time, the order in which you put the columns for P does not matter. But once you pick the order for the columns for the P, you've picked where you're putting the eigenvalues. Okay, so if you put this negative 1, 2, 0, say in column 2, then you're going to put the 2 in the 2, 2 spot there in your diagonal matrix. Any questions on that one at all? Are we okay with that? That looks like what we did last time, right? Okay, so... Yes, good. Thanks. I love the delay. It cracks me up. I don't know why. All right, so let's talk a little... It makes me laugh every time, and I don't know why it makes me laugh. All right, so let's talk about this idea with the multiplicities. So we saw that the eigenvalue 3 in the previous example had a multiplicity of 2 because we had that lambda minus 3 squared. So that's what we refer to as the algebraic multiplicity. So it's the power on the factor that gives the eigenvalue. Or said in a more algebraic way, it's the multiplicity of the eigenvalue as a root of the characteristic equation. You've talked about, well, at least you should have talked about multiplicities before in Algebra 2 class or in a pre-calculus class or college algebra class. The multiplicity is just that power on the factor that gives you the root. So in that previous example, the multiplicity of lambda equals 2 was 1 because the power on the lambda minus 2 factor was a 1. The multiplicity of 3 was 2 because the power on the lambda minus 3 term, or factor I mean, was 2. Okay. So algebraic multiplicity is the multiplicity that you're used to. Geometric multiplicity is the new one, and that's just the dimension of the eigenspace associated with the eigenvalue. That's geometric multiplicity. Or, said a little bit more plainly, I guess, it's the number of free variables in the reduced row echelon form when you plug in the eigenvalue. And so the number of free variables gives you dimension of the eigenspace. So in the previous example again, with the eigenvalue 2, it had algebraic multiplicity 1. It also had geometric multiplicity 1. For the eigenvalue 3, we had multiplicity 2 algebraically and geometrically. Now the relationship between the two of these is that your algebraic multiplicity we're not going to prove this, but the algebraic multiplicity is always greater than or equal to the geometric multiplicity. We run into trouble if the algebraic multiplicity is strictly greater. If the algebraic multiplicity is strictly greater than the geometric multiplicity, your matrix will not be diagonalizable. So I'm going to summarize that in a statement at the end. I'll come back to that, but let's do an example where we get a matrix that's not diagonalizable. And so let's look at this next example, and then I'm going to come back to this relationship. So if what I just said doesn't make a lot of sense right now, I promise I'm going to come back to it here in a minute. Okay? All right, so same idea here. Set up our characteristic equation. This is another one of those where I set up where the determinant's not so hard to take. Well, I say that now. Watch me screw it up. So I can expand along that last column because I got a couple of zeros there. The 5 minus lambda again is a plus, so then I get 5 minus lambda out in front, and then I've got that submatrix up there in the upper left-hand corner. When I get it to a 2 by 2, the determinant is pretty easy to take. Now let's let's expand inside that second set of parentheses and then refactor. Got a lambda squared. Looks like I got a plus 4 lambda. And then I've got a, that's interesting. Did I make an error somewhere? This is not doing what I want it to do, because this isn't going to refactor the way it's gone. Right? It's...
I think is it a minus?
Negative 10.
Oh, good grief. Thank you. Thank you. Made my life a lot simpler. I was like, that wasn't going to factor. Minus 7 minus 4. I don't know where I got plus 4. Holy cow. 7 times 3 is 21 plus 4 is 25. Okay, that's much better. Okay. Sorry about that. Thank you. Now this should factor as lambda minus 5 squared, and I've got an extra lambda minus 5 in here. So this actually is negative of lambda minus 5 cubed. And so we only get lambda equals 5 as our eigenvalue, the only eigenvalue that we have here. Like, I knew I was doing something wrong because I rigged this problem so it would come out this way. When I made up the problem, I rigged it so it would come out. So I knew I screwed something up. I told you I could screw up the determinant. All right, so here we know that the algebraic multiplicity is 3, because we see that power of 3 on that lambda minus 5 factor. All right, so if we go through the row reduction now, for your lambda equals 5, we would get 2, negative 4, 0. I would have 1, negative 2, 0. And I have, what, negative 2, 0, 0 here.
Negative 2, 5, 0.
Negative 2, 5, 0. Good grief. Oh, maybe I should just quit now. All right, so certainly the second row will kill off the first row. If I do negative 2 times the second, add it to the first, I get a row of zeros, without a doubt. If I do 2 times the second row and add it to the third row, I'll get 0, 1, 0. And then I can get a 0 here. So I think your reduced row echelon form here should look like this.
Yes.
Yes, good. Thank you. Maybe I should have opened up the calculator app, man. It would have been a lot easier. All right. So, now we notice that we only have one free variable. Your eigenspace here will be 0, 0, 1 times that t. So any multiple of 0, 0, 1 is an eigenvector associated with lambda equal to 5, but we only have one linearly independent eigenvector here. We only have one linearly independent eigenvector. So that tells us that our geometric multiplicity is just 1. And this is what I was mentioning before, that when your algebraic multiplicity, which in this case is 3, gets bigger than your geometric multiplicity, you get in trouble because you don't get enough linearly independent eigenvectors to form a square matrix. We only have one eigenvector here. So I cannot form that matrix P that's invertible. Remember, we need an invertible matrix P. in order to get an invertible matrix, I need linearly independent eigenvectors, which I don't have here. I don't have 3 linearly independent eigenvectors for this particular matrix. I only have 1. So we cannot diagonalize. The conclusion here is we cannot diagonalize A because we cannot find 3 linearly independent eigenvectors. And again, the reason why we couldn't find enough linearly independent eigenvectors is because the algebraic multiplicity of lambda equals 5 is greater than the geometric multiplicity. And again, that's all you have to say at that point. If you find it, by the way, if you find one eigenvalue for which this is true, you know that you cannot diagonalize. We need to have the algebraic multiplicity equal the geometric multiplicity for every single eigenvalue in order to be able to diagonalize. So I'm going to actually write that down too. So in order to diagonalize a matrix A, the algebraic multiplicity must equal the geometric multiplicity for every eigenvalue of A. If you get even one where they're not the same, then you cannot diagonalize. Any questions on that at all? Cool. All right. Like I mentioned at the beginning here, I do want to do one more test before final. And by the way, as far as your quote-unquote final exam, it's just going to be a shorter test, essentially, over the stuff that we're going to cover starting on Monday, which is over Chapter 8. I'm not going to do a comprehensive final. I'm just going to do a shorter one, and the entire thing will be take-home, so you don't have to worry about trying to do an in-class timed portion. So your final exam is less of a final exam than a typical one would be. It'll just be over the Chapter 8 material that we cover, which, like I said, I'm going to start on Monday. But your final won't be comprehensive, and it'll be take-home. So I do want to do your test, though, for this next week, like we did the last one, where part of it will be kind of the in-class part, and then part of it will be take-home. So let me talk a little bit about what I'm thinking about the split for that, and in particular, let's talk about the in-class part, because I'm guessing that's probably the one that you would be more worried about. And this one, I really do want to make more of the computational variety. So there will be, like the last one, we'll do the 5 true-false, just like the last exam had. Your first problem on the last homework, I think it was I gave you a matrix and you had to figure out the row space, the column space, the null space, and some orthogonal complements. So that would be a problem just like that would be something that would be on the test. So being able to get your matrix entered and row reduce and interpret the appropriate row reductions. Then we had some computations with inner products. So I'm thinking, well, you had a problem that had a table on the last homework, so that could be something that might be on there where I give you a table of values and then ask you to do a couple of inner products that way. Also being able to do magnitudes, angles, projections. Again, very computational things. And I'm not on this part. I would not be asking you to prove something is an inner product space or anything along those lines. This is literally, can you do the computations? And then the last part, as far as computations go, would be find eigenvalues, eigenvectors, and diagonalize. As far as the in-class portion goes, that would be it. Very, very, like I said, very, very, very computational. Can you do the computations that we've talked about since the last test? You've had homework on the first parts here, the first two parts here, and then this stuff is obviously on the homework that you're doing now. Okay. I know that there are other computational things, but the other computational things you have to do, I think, are longer. So I don't want to put that on the in-class exam. These are kind of the basic computational things that you have to do. So then your take-home exam, which I will get to you, I'll probably have that ready for you on Monday. And then do Friday. Give you a little extra time to work on it. This one will have prove something is an inner product. This is where I'll ask you about, say, Gram-Schmidt. Going through the Gram-Schmidt process for a set of vectors. That's on your current homework now. Compute a least squares model. That's also on your current homework now. And then there'll be a couple of proofs involving inner products and eigenvalues and eigenvectors. That's how I'm going to split up the material for your exam. And then, like I said, as far as a quote-unquote final, we're going to start talking about stuff from Chapter 8 Monday. My goal is to get through the first 4 sections of Chapter 8. Just trying to let you know where I'm thinking the rest of the semester is going. My goal is to get through the first 4 sections of Chapter 8. And then I will give you a completely take-home test just over the Chapter 8 material. That will be like I said, your quote-unquote final exam. That'll be it as far as I go. So there won't be an in-class portion. and it won't be comprehensive. It'll just be over the last stuff. I think the semester has been weird enough that I don't need to make it harder at the end. So, any questions about that at all?
So if this whole pandemic thing wasn't going on, where would we have gotten to at the end of the semester?
Section 8.4. Okay. Actually, it's really weird. I am actually going to get done with everything I would have covered anyway. There's usually a topic that I will cover. You know how I've mentioned this idea of discrete dynamical systems and Markov chain stuff? I would have actually spent a week talking about Markov chains and doing that application of eigenvalues and eigenvectors because it's very, very applicable to biology and finance and anything that has to do with game theory. There's lots and lots of applications to Markov chains, which is why I would have done that in this class. So that's the part that I cut out.
Sounds good.
Yeah, we actually did a good job. You've actually done very well getting through the material. I'm very pleased as far as that goes, especially doing with all this craziness going on in the world. It's been nutty, and I don't appreciate it. But I do appreciate you all working so hard and getting through this material. I'm impressed with how you've been able to cope. At least with my class, I can't obviously speak for how you're coping with other things, but at least for how you've coped with my class, I'm very impressed. So thank you for working hard for me. I really do appreciate it. It makes my job easier.
Thank you, Dr. Joe.
Yeah.
I just had a quick question about the final.
Sure.
Are you gonna do kind of like what you're doing on this take home, where you'll like post it the Monday of finals week, and then it'll be due that Friday?
I will. I probably won't have it wait till that next Friday. What I probably will get it posted. I'll see how next week goes for how we're getting through the material, but I will probably post it either next Friday or the following Monday. So actually, while we're still doing stuff, and then have you turn it in probably by Wednesday of finals week. I want to give you a little bit more time to do it, and then not necessarily have to wait until the very, very end of finals week to get it done either. So I'll probably give you at least a week, if not more, and get it to you before the end of the semester.
Okay.
And then we don't have any more homework?
Good question. I was thinking about doing... what I might do is just do practice problems and have the solutions up so that you can see if you want to practice through them before the final pops up. That probably makes more sense. And that way you can get feedback immediately on it rather than waiting for me to get it graded. Does that work for you?
Sounds good.
Okay.
Yeah.
Okay. Any other questions at all? All right, like I said, I was going to get it done a little bit early today anyway, so if you got questions on homework, of course, give me a holler. Otherwise, starting on Monday, we will get into Chapter 8 and get the semester finished up. Like I said, though, thank you, everybody, for working as hard as you are. I do really appreciate it. Have a good weekend, everybody.